Hi, in this video we will solve a problem of an incompressible liquid which is having a laminar flow through a horizontal pipe. The pipe has different diameters at the inlet, at section A and section B. The inlet conditions are defined in terms of pressure and velocity. We have to find out the pressure at section A and section B. You can also see a small animation on the right hand side. We take a quick look at the Bernoulli's equation before solving the problem. We have three terms in it: the pressure, which is an energy per unit volume; the potential energy per unit volume, which is rho gz or rho gh, we can use either one; the kinetic energy per unit volume, which is half rho b squared. So the sum of these three terms at a section A will be equal to the sum of these three terms at section B, at section C, and so on. In this way, the energy per unit volume is conserved in the flow of a liquid through a pipe. For more details on Bernoulli's equation, see one of my other videos. The problem mentioned a horizontal pipe. When we see the sketch in front of us, it's clear that the center line passing through the various sections is at the same height from a given datum plane. All the sections are at the same height. So the potential energy term in the Bernoulli's equation becomes constant. We don't have to solve for that, so we will only be concerned with the fluctuations in the pressure and the fluctuations in the kinetic energy from section to section. We now write the Bernoulli's equation with only pressure and kinetic energy terms. So P inlet plus half rho into V inlet whole squared will be equal to P at section A plus half rho into V A whole squared, and so on. Now, in this equation we know the pressure inlet, we know the velocity at the inlet, we know the density as well, but we do not know the V at section A. We don't know the velocity. So with two unknowns we cannot solve the equation 1. So we have to find out VA, and the way to do that is to use the continuity equation, because we have the area and at least we can find out the area at section A. So A1 V1 equal to A2 V2, or A inlet into V inlet is equal to area at section A into velocity at section A. And using pi r squared, we can find out the area at section A. With that, as you can see, we can find out the velocity at section A as 1 meters per second. This we plug in into equation 1 and we can find out the PA. We now substitute into the equation. On the left hand side you have P inlet 2 atmospheres plus half rho into 4 squared. On the right hand side you have PA in atmospheres plus half rho into 1 squared. Rearranging that, you get PA as 2 atmospheres plus a term half rho into 4 squared minus 1 squared. That's 16 minus 1, that's 15. Rho is 1000 kg per meter cubed. So half into 1000 into 15 is 7500. The only important thing is you cannot add 2 plus 7500. It's 2 atmospheres and the other term is 7500 Newton per meter squared. So we have to either convert everything into atmospheres or everything into Newton per meter square, and only then we can add them. 1 atmosphere is equal to 1.013 into 10 to the power 5 Newton per meter squared. And therefore 7500 Newton per meter square can be divided by 1.013 into 10 to the power 5, and we can find out how much atmospheres it is equivalent to. Then you can add 2 plus that. Just for information, we have given in blue color why the kinetic energy term has the units Newton per meter square. You can go through that slowly. Density here is kg per meter cubed, velocity is meters per second. So when you do rho into v squared, finally you will get Newton per meter square. You can go through that. we now convert 7,500 Newton per meter squared. We divide it by 1.013 into 10 to the power 5 Newton per meter squared, and we will get 0.074 atmospheres. We can now add this to the two atmospheres and we will get pressure at section A as 2.074 atmospheres. We now move on to section B, where we have to find the pressure at section B. We have to find out the velocity at section B anyway, so we apply the continuity equation. A1 V1 is equal to A2 V2, and using the similar way in which we did for section A, we can find out the velocity at section B, VB, as 11.11 meters per second. This makes sense because the section B is very thin, it's only 3 centimeters in diameter, so the velocity should be faster, which is what we are getting. We now substitute VB into the Bernoulli's equation for pressure and kinetic energy at all points. On the left hand side you have 2 atmospheres plus half rho into 4 squared as the total energy at the inlet of the pipe. At section B you have PB in atmospheres plus the term half rho into 11.11 whole squared. Rearranging that, you get PB as 2 atmospheres plus half into rho into 4 squared minus this 123.43. That becomes negative. So very soon you get 2 atmospheres minus a term, which is in Newton per meter squared. That's the 53,715. After this, we have to convert the Newton per meter squared into atmospheres. So we have divided 53,715 divided by 1.013 into 10 to the power 5, and so we get the term 0.53 atmospheres. So 2 atmospheres minus 0.53 atmospheres is 1.47 atmospheres. The negative sign makes sense because the diameter is smaller than the inlet, therefore the pressure should be lower than the pressure at the inlet. So now we have the answers for the pressure at section A and section B. I hope this video was useful for you. Please do subscribe to our channel, share it with your friends, download the app Physics Models or log into our website. Have a good day and bye-bye.